Hello everyone. So today I will start with the next topic, that is precision and accuracy. Uh, so we have switched from the handwritten notes to the book because it will help you to when you will revise the lectures and consult your book again. I think it will help you more. So that's why I think switching from the handwritten notes to the book is better. I'll highlight most of the points that are important, and I think that will help you. I'll post the annotated book later on, or you can email me and I can send you there. So let's start with today's topic, that is precision and accuracy. So precision and accuracy are most commonly used terms that are again confused. Students are confused about. Precision and accuracy seems similar words, but they carry different meaning. If we talk about precision, then it's more related to instrument. So the absolute error or absolute uncertainty in an instrument is basically equal to least count of that instrument, and that least count is basically defines the precision of that instrument. For example, the absolute uncertainty for the meter tape would be different, and for absolute uncertainty for the screw gauge or vernier caliper would be different. So their least counts would be different, and ultimately their precisions would be different. Uh, the more the more smaller least count is, the more precise an instrument is. So in comparison, if I would say that vernier caliper is more precise than meter tape, and if I compare vernier caliper with the screw gauge, then I would say that screw gauge is more precise than the vernier caliper. But that does not mean that the measurements taken with the help of screw gauge are better than vernier caliper, or they are better than the meter tape. It purely depends upon the application where you are using. For example, a measurement of the road is most of the time you measure the difference between the two cities in kilometers, right? So in that case, you cannot measure it using a vernier caliper, or you cannot measure it using a screw gauge. But when you are measuring a diameter of a wire, in that case, it's better to use even screw gauge instead of vernier calipers. So it all depends that what you are measuring, and the accuracy is basically then purely subjective. Sometimes the measurement taken by the help of meter tape is more accurate, and the measurement taken by the vernier caliper is less accurate, because the percentage error in the measurement describes the accuracy of the instrument. With that said, we can now uh, move to the concepts that the author of this book wants to deliver. So, as I said, that the absolute uncertainty is equal to the least count. So in that case, in this case here, for example, the least count of an instrument is 0.1 centimeter, right? So this is the absolute uncertainty, the accuracy. And the fractional uncertainty, for example, you measure a length that is 25.5 centimeter, and then the uncertainty or absolute uncertainty or the precision of that instrument is 0.1. So you take the fractional uncertainty by dividing the measurement that you got, the reading that you got, with the uncertainty, and you'll get the answer equal to 0.04004. When you convert it to the percentage, then the percentage uncertainty comes out to be 0.4%. So here we are comparing two measurements: a measurement that has a least count of 0.1 centimeter, and what is the instrument of that? I think it's a meter tape, but later on, yeah, it's a meter rod. So the first case is this, where we have let me do it let me change the color, I think, to green. So with meter rod, you are taking this first measurement, which is 0.1, which has an absolute uncertainty of 0.1 centimeter, and its percentage uncertainty is 0.04, and its fractional uncertainty is 0.004. You attempt to take another measurement that is measured using a vernier caliper. Now we change the color to light blue, and we can say that with the vernier caliper, the least count is 0.01 centimeter. Now 0.01 is less than this 0.1. So this measurement taken with the help of vernier caliper is now more accurate, that is 0.07 centimeter. Now let's look at the absolute fractional uncertainty and percentage of the second measurement. So it's recorded as 0.45 centimeter. Now we change this measurement to the percentage of fractional uncertainty. So with fractional uncertainty, it's 0.02, and with percentage uncertainty, it's 2%, right? So now you can see that the precision of this instrument is better, but the percentage error that you got is more here and is less here. That means this first measurement was less precise, but more accurate. And I think I would write it out. So the first measurement was less precise, but more accurate as right. So the second measurement is more precise, less precise. The second measurement is more precise and less accurate. So just one sec. Yeah. Okay. So with that said, we can come to this last part of definition. This says the same thing that I have written just over here. So it's the same thing. So it says that a precise measurement is the one which has less absolute uncertainty, or an accurate measurement is the one which has less fractional or percentage uncertainty. So now keep in mind that if the let me color code it. So if you say that the measurement is accurate, then in that case it must have less fractional uncertainty or less or percentage uncertainty. But on the other hand, if you say that the measurement is precise, then that should have a least absolute uncertainty. With that, there are few rules over uncertainty. I mean, how much uncertain, or how much how to interpret your result when it is in the form of addition, subtraction, multiplication, etc. So uncertainties are added or subtracted in case if you are measuring if you are adding two measurements, then in that case the total uncertainty is the addition of the two. For example, here you have one measurement x1 that is 10.5, that has absolute uncertainty of 0.1 centimeter. Similarly, another measurement that has an absolute uncertainty of 0.1 centimeter. Then you can add these two uncertainties, and the total uncertainty in the whole measurement would be 16.3 plus minus 0.2 centimeter. Now it's not dependent upon whether you are adding or subtracting. So either it is addition of these two terms or subtraction. In both cases, the uncertainty would be plus minus 0.2. It's the tolerance between the minimum and maximum values of the sum that you will have in the end when you are adding the two quantities. Now, in case for the multiplication or the division, let's say we have a good formula for the resistance, that is VR is equal to V over I. So in that case, the percentage uncertainty is added. So for example, with V, that is voltage, you have a uncertainty of 0.1 volt, and with the I, you have uncertainty of 0.05 ampere. In that case, the percentage, now you have to deal in percentages, right? So the percentage uncertainty for voltage would be 0.1 divided by that. Remember, when we are talking about the percentage uncertainties, in that case, we'll divide the least count by the measurement that we have in hand. For example, the least count is 0.1 and the measurement that we have in hand here is 0.5.2. So you will divide 0.1 by 5.2 and the answer you will get, and multiply that to 100 to get the percentage uncertainty to be 2%. Similarly, for I, you'll do the same. You have this uncertainty, you have this uh, reading or your current value at hand, and then you'll divide these two and you'll get out an answer to be equal to absolutely about 6%, right? Okay. So the total uncertainty in this case would be addition of these two percentage uncertainties. So let's say the percentage uncertainty coming from this is 2 and from this is 6, then R is equal to 5.2 divided by this is, from here you'll get the value of resistance, right? And then you'll say that the overall value of resistance, which is 6.1 ohm, is has an uncertainty of 8%, right? So the what is 8%? Actually 8% is the 8% of this 6.19. So if you calculate 6.19, 8% of this 6.19, you will come up with the value of 0.5 ohms. So three steps in case it is a division or multiplication. First, you will find the absolute uncertainties. Let me write it. I think, yeah, yeah. So so first you will find absolute percentage uncertainty, and let me reduce the size, and then second you will find the, you will add those uncertainties, add percentage uncertainties, and at third multiply total percentage uncertainty with the result. For example, 0.08 into 6.19. So you will get 0.5, and then you will call it that this is the percentage uncertainty between between the total reading. So that is the rule for the multiplication and addition. Now there is another variation that comes with the power factor, and that is now in that case you have to multiply that percentage uncertainty by the power. So how? Let's say we have this V is equal to 4 by 3 pi r cube, which is the formula for the volume of the sphere. and we can say that the percentage uncertainty would be now the multiplication, like the power is 3, so this x would be the uncertainty in r. So you will multiply the uncertainty in r with the power that we have, and you'll get the uncertainty then in volume. For example, here in this case, the percentage uncertainty or the uncertainty in this, the absolute uncertainty in in r, which is the radius, is 0.01. So the absolute uncertainty or least count is again 0.01 centimeter. You'll convert this to percentage uncertainty, which is 0.04. Convert this thing. This is 0.4%. And now the total uncertainty would be that percentage uncertainty, this one, multiply this 3. Where this 3 is coming, this is coming from this power. So you'll multiply that power with the percentage uncertainty and you'll get the answer, which is 1.2 here in this case. So now you'll calculate the volume, and similarly with the volume, after calculating the volume, you will find the 1.2% of this total volume. So for that, you will simply multiply 0.012. You will convert that percentage to fraction, and you will multiply that fraction 0.012 to this reading, and then whatever you get, you'll add and subtract it in the final answer, and you'll say that my reading is plus minus this with this much uncertainty, right? Then here comes the uncertainty in the average measurements. So you'll find the average of all the values that you measured first. So it is, again, there are a few steps that you need to follow. First, you will find the average, obviously. And then you'll find the deviation from the mean or the average value. Let's say you have three values, 2, 4, and 6. In that case, your mean value is 4, and you will calculate the difference of each value from the mean. So here comes the example. Let's look at the example. Is You have got the readings of 1.20, 1.22, 1.23, and similarly all these readings are coming from the measurements that you have made using a micrometer screw gauge, right? So you have these measurements. Now you'll first find the average of these measurements. Here is your average. There you go. Here is your average. Average is 1.21. Now you'll calculate the difference of this average from each value. For example, this is 1.20. So you will calculate 1.20 minus 1.21 and you will get 0.1. You'll find the absolute value, not the it's not, you'll not take care of the sign here. So if it's 1.20 or if it's 1.22, it would be 0.1, not 0 minus 0.1 in any case. So you'll disregard signs here. So it would be 0.01, 0.01, similarly all values here, and add them. Then divide it with the number of the observations that you have. For example, in this case, 1, 2, 3, 4, 5, 6. So you have 6 number of observations. You will divide it with number of observations, right? So let me write it. I think it will clarify number of observations. Okay. So after getting this mean deviation, this is 0.01. So you can say that the uncertainty in the measurement, in the average measurement 1.21, is actually this one, that is coming from the mean deviation 0.01. So your answer would be like 1.21. That is the average of all the measurements, plus minus the mean deviation that you calculated by adding all the differences and then dividing by the number of the observations. So you'll come up with this answer. Now this will come handy when you will have some experiments in practicals. or when you are doing some numerical problems, this fifth portion will become handy. And you'll see in lab work, when you are doing experiment for the pendulum or some other instruments, when you are handling some other instruments that require some time measurements. In that case, you'll have to add and subtract some uncertainties and things like that. In that case, this portion will be helpful. So there are different tools to add or subtract the uncertainty in when measuring times. So let's say you measure time that is 54.6 seconds. Straight away come with the example. Let's go with the example. So you have this measurement 54.6 seconds, and the total number of vibrations. It's a experiment that is for the vibration of something. So one vibration is basically the complete motion from one peak to another peak and then coming back to the original peak. So it would be like to and fro motion of pendulum. So anyways, for 30 vibrations, you noted the time to be 54.6 seconds. And then you'll find out, first you will find out the time for the one vibration. That would be the total time divided by the number of vibrations. So this is the number of vibrations. Let me write it for you. Here, I think I can write it bottom. Number of vibrations. Okay, so these are the number of vibrations, and you'll find out it's 1.82 per vibration. So time of one vibration is 1.82 seconds. So the uncertainty would be the uncertainty in one vibration, that is 0.1 second, divided by the uncertainty and divided by number of vibrations that you have. So here you have 30 vibrations. So 0.1 divided by 30, it's 0.003. So you'll get out an answer of 1.82 plus minus 0.003. So that is the uncertainty in time. These are very straightforward. If you'll go back and revisit what I said, give it 10 to 15 minutes, and you'll all the things would be on your fingertips. When we'll study the next lecture, we'll see through the examples and we'll discuss various concepts that we discussed in this lecture. So till then, bye bye. See you in next lecture. Thank you.